This is lab 3, where we will look at a black hole. The goal of this lab was to find the mass of the black hole by analyzing the motion of the orbiting star. The star orbiting the black hole has a trajectory which was determined by my specific email address, and the star's motion was used to find the net force on the star by the black hole. So now we're going to look at our fundamental principles. So we use Newton's second law as well as the rate of change of momentum. As you can see, F net is equal to dp dt. They can be broken up into components, so F net parallel, F net perpendicular, dp dt parallel, dp dt perpendicular. The parallel component is equal to d magnitude of p dt times p hat. The perpendicular component is the magnitude of p dp hat dt. We also use Newton's law of universal gravitation, which is F net g times m1 times m2 divided by magnitude of radius squared times r hat. In this case, the mass is the mass of the black hole and the mass of the star are initial conditions. So the universal gravitational constant, our star's mass, and the time between points was equivalent to 1 Earth day, which is 86,400 seconds. Our system was a star, our surroundings was the black hole. So now we're going to look at the code in GlowScript. So this seed was my email address, which determined the trajectory of the star. This is the gravitational constant, the star's mass, the time between intervals. This determined the displacement of the x component. This was the velocity of the x component. This was the displacement of the y component. And this was the velocity of the y component. In this new section of code, we use a while loop to find the net force. In this while loop, we calculate the initial and final velocities using both our x and y components from the previous code. We also find the initial and final momentum. We then can find the change in velocity as well as the change in momentum. By using the change in momentum, we can find the rate of change in momentum, dp dt. Because of Newton's second law, we can set F net equal to dp dt. Now we solve for the parallel component. So we calculate p hat as well as d magnitude of p dt. And then we get the parallel component, set that equal to F net parallel. Now we're solving for dp dt perpendicular. Because we already have dp dt and dp dt parallel, we can just subtract them from each other to get the perpendicular component. From there, we set F net perpendicular to dp dt perpendicular. So in this final part of our code, we used it to solve for the mass of the black hole. Seen here, the star's position is just our radius between the star and the black hole. The law of universal gravitation was used in order to determine this mass. However, if we were already given the mass of the black hole and the mass of the star, we would use this formula in order to find F net. So using the law of universal gravitation, we just calculated it out in order to find the mass of the black hole, and you get that the magnitude of F net times the magnitude of the radius squared divided by g times mass of the star is just equal to the mass of the black hole. So now let's look at our computational model of the star and the black hole. There are 3 different force vectors. The orange vector is the net force. It's always going to be pointing towards the black hole. The pink vector is the perpendicular component of net force. It causes the star to change direction. And the blue vector is the parallel component of net force, which causes the star to slow down or speed up. Looking at these 2 different figures, we can see that when the star is moving towards the black hole, the momentum and the parallel component of net force are in the same direction, causing the star to speed up. When they are moving away from the black hole, they are in opposite directions, causing the star to slow down. So here we take a look at the results. We find that the mass of the black hole is this, the net force is equal to this, the net force of the parallel component is equal to this, and the net force of the perpendicular component was equal to this. So now we're getting into the questions. So for the what does this mean question, it's asking how is the net force and its parallel and perpendicular components are different from the rate of change in momentum and its parallel and perpendicular components. So here's the net force, and this is the rate of change in momentum. And these are the 2 components for net force. These are the 2 components for the rate of change in momentum. As you can see, they are similar, they are equal to each other, however, they are not the same. They can be found different ways. Net force can be found using the law of universal gravitation. The rate of change in momentum can be found using mass times velocity. So now for the what if question. So it was asking us if the black hole was removed and another black hole took its place, what's going to happen is the mass going to change. Well, the answer to that is no. There's not going to be a different mass because the mass is determined by the motion of the star, and if the motion of the star is not being changed, then therefore the mass will not change if there's a new black hole created instead in that place.